DS-Lite on FortiGate Introduction. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series we are going to explore DS-Lite, which stands for Dual Stack Lite. DS-Lite is a transition technology developed to help internet service providers manage the exhaustion of IPv4 addresses while progressively migrating their networks toward IPv6. The challenge ISPs face is significant. The public IPv4 address pool managed by ICANN was officially exhausted in 2011. Regional registries like ARIN, RIPE, and APNIC have been issuing the last of their allocations for years. ISPs that want to connect new subscribers must now find creative solutions to accommodate IPv4 traffic without consuming scarce public IPv4 addresses. DS-Lite is one of the most elegant solutions to this problem. Rather than giving each customer a dedicated public IPv4 address, DS-Lite allows the ISP to build an IPv6 only access network. Customer devices still send IPv4 traffic, but at the edge of the customer network, that IPv4 traffic is encapsulated inside IPv6 packets and tunneled across the ISP's IPv6 backbone to a centralized gateway called the AFTR, which stands for Address Family Transition Router. The AFTR is where the IPv4 addresses actually live, and it performs NAT on behalf of all connected customers. FortiGate supports DS-Lite natively, allowing it to act as the B4 element on the customer premises side of the architecture. In this video series we will walk through every aspect of DS-Lite theory and FortiGate configuration in detail. DS-Lite architecture components. Let me walk you through the DS-Lite architecture diagram in detail. The architecture has three major zones separated by two key functional elements. Starting from the customer side, we have the customer premises equipment, or CPE. In a FortiGate deployment, the FortiGate appliance itself acts as the CPE. The CPE has two logical functions in DS-Lite. It is the endpoint for regular IPv4 traffic coming from the LAN, and it is where the B4 element runs. The B4 element, which stands for Basic Bridging Broadband, is the software function responsible for taking IPv4 packets and encapsulating them inside IPv6 packets for transport across the ISP network. The B4 element connects to the ISP access network. This network is IPv6 only. No IPv4 routing exists here. The ISP has provisioned this segment entirely with IPv6 addressing, and all customer tunnels traverse this segment encapsulated within IPv6. This is a critical architectural point because it means the ISP does not need to allocate any IPv4 addresses for the access network infrastructure itself. At the far end of the IPv6 access network sits the AFTR, the Address Family Transition Router. The AFTR performs two functions simultaneously. First, it is the IPv6 tunnel endpoint that receives the encapsulated packets from the B4 element and decapsulates them, extracting the original IPv4 payload. Second, it performs NAT44, translating the customer private IPv4 addresses to public IPv4 addresses before forwarding traffic to the IPv4 Internet. The IPv4 Internet is the final segment. This is the regular public IPv4 network that all customer traffic ultimately needs to reach. The AFTR maintains a pool of public IPv4 addresses and manages the NAT mappings for all connected DS-Lite customers. Return traffic from the Internet arrives at the AFTR, which performs reverse NAT and re-encapsulates the IPv4 response inside IPv6 before sending it back through the access network tunnel to the correct B4 element at the customer premises. FortiGate DS-Lite prerequisites. Before you can configure DS-Lite on a FortiGate, several prerequisites must be in place. This slide summarizes all the requirements you need to verify before touching the FortiGate configuration. Skipping any of these verification steps is the most common cause of DS-Lite deployment failures. The first prerequisite is FortiOS version compatibility. DS-Lite support was introduced in FortiOS 6.2 and has been available in all subsequent releases including 6.4, 7.0, 7.2, and 7.4. You should always run the latest supported release for your hardware platform to ensure you have the most recent bug fixes related to tunnel handling and IPv6 support. You can verify your FortiOS version by running the command get system status from the CLI. The second prerequisite is that your ISP must provision your WAN interface with an IPv6 address. DS-Lite fundamentally depends on IPv6 connectivity for the tunnel transport. The ISP typically assigns this IPv6 address dynamically via DHCP version 6. Some ISPs use Slack with a delegated prefix instead. You need to confirm with your ISP which mechanism they use and obtain the WAN IPv6 address before proceeding. The third prerequisite is knowing the AFTR IPv6 address. This is the destination address that the FortiGate will use for all DS-Lite tunnel packets. The ISP usually provides this address through DHCP version 6 option 64, which is defined in our FC 6334 specifically for DS-Lite AFTR discovery. In some deployments the ISP provides this address in their provisioning documentation and you configure it statically. You must have this address before configuring the FortiGate. The fourth prerequisite is planning your LAN IPv4 addressing. Since the AFTR will perform NAT for all customer traffic, your LAN can use any RFC 1918 private addressing scheme. The standard recommendation is to avoid the 100.64.0.0/10 range, which ICANN has reserved for CGNAT shared address space and some ISPs use internally, as it can cause routing confusion. Creating the DS-Lite tunnel interface. The core of the DS-Lite configuration on FortiGate is the tunnel interface. This is a virtual interface that represents the IPv4 in IPv6 tunnel between the B4 element on the FortiGate and the AFTR at the ISP. All IPv4 traffic that needs to travel over the DS-Lite connection is routed through this tunnel interface. You create the tunnel under Config System Interface and give it a logical name. In this example we use DS-Lite tunnel, but you can name it anything meaningful for your deployment. The name is significant because you will reference it later in route and policy configurations. The setType DS-Lite command is what tells FortiOS that this is a DS-Lite tunnel interface rather than a regular interface or a different tunnel type. This is a critical command because it activates the DS-Lite specific encapsulation logic, meaning FortiOS will apply IPv4 in IPv6 encapsulation to packets entering this interface rather than treating them as normal traffic. The set remote IP6 command specifies the AFTR IPv6 address. This is the destination address that will be placed in the outer IPv6 header of all encapsulated packets. You must enter the exact IPv6 address provided by your ISP. An incorrect AFTR address means the tunnel packets will be sent to the wrong destination and DS-Lite will not work. The set interface WAN1 command tells the DS-Lite tunnel which physical interface to use as the underlying transport. This must be the WAN interface that has the IPv6 address configured in the previous step. FortiGate uses this binding to determine which IPv6 source address to use when building the outer IPv6 header for encapsulated packets. The set IP10.0.0.255.255.255.252 command assigns a local IPv4 address to the tunnel interface. RFC 6333 specifies the 192.0.0.0/29 range as the well-known prefix for DS-Lite interface addressing. The address 192.0.0.2 is the standard B4 element address in this range. This inner tunnel address is used for local routing purposes and is not visible to the Internet. Verifying DS-Lite connectivity. After completing the configuration, systematic verification is essential to confirm that DS-Lite is working correctly at each layer. The verification follows a layered approach, starting from the lowest layer, which is IPv6 reachability, and working up to full end-to-end IPv4 connectivity through the tunnel. The first verification step is checking IPv6 connectivity from the FortiGate WAN interface to the AFTR. You run the command execute ping6 from the FortiGate CLI with the AFTR IPv6 address as the target. If this ping succeeds, it confirms that the ISP has provisioned IPv6 correctly, that the FortiGate has received a valid IPv6 address, and that basic IPv6 routing between the FortiGate and AFTR is functioning. If this ping fails, you must resolve the IPv6 layer before proceeding. Common causes of failure here are the WAN interface not receiving an IPv6 address from DHCPv6, incorrect AFTR address, or ISP routing issues. The second verification step is checking the tunnel interface status. The command diagnose netlink interface list DS-Lite tunnel shows the operational state of the tunnel interface. You are looking for the interface to show as up in both the administrative and operational sense. If the interface shows as down, review the tunnel configuration to ensure the remote IP6 and interface parameters are correct. The third step is verifying the routing table contains the DS-Lite default route. Running get router info routing table all shows all active routes. You should see an entry for quad 0/0 pointing to the DS-Lite tunnel interface. If this route is missing, check your static route configuration and verify the tunnel interface is up, as FortiOS typically removes routes associated with down interfaces. The final verification is a full end-to-end connectivity test. Running execute ping 8.8.8.8 from the FortiGate CLI tests whether IPv4 traffic is successfully being encapsulated, traversing the tunnel, being de-encapsulated and NAD at the AFTR, and reaching the public internet. A successful ping to a reliable public IP address confirms that all components of DS-Lite are functioning correctly. DS-Lite troubleshooting and common issues. Even with a careful configuration, DS-Lite deployments can encounter issues. This slide covers the most common failure modes and the diagnostic approaches for each one. Understanding these failure patterns will save significant troubleshooting time in production deployments. The first and most common issue is no IPv6 address on the WAN interface. DS-Lite cannot function at all without this. The diagnostic command diagnose IP6 address list shows all IPv6 addresses currently assigned to all interfaces. If the WAN interface is not listed or shows only a linked local address starting with FE80, it means DHCP version 6 did not succeed. You should verify the ISP has provisioned the line for IPv6. Check whether the WAN interface mode is set to DHCP6, and use diagnose debug application DHCP6C-1 to capture DHCP version 6 client activity in real time. The second common issue is an incorrect AFTR address. If the AFTR IP version 6 address entered in the tunnel configuration is wrong, the encapsulated packets will be sent to the wrong destination. You can verify this using the packet sniffer. The command diag sniffer packet WAN1 Prota 41 inches 40 will capture all protocol 41 packets on the WAN interface. Protocol 41 is the IP protocol number for IPv4 in IPv6 encapsulation. Examining the destination IPv6 address in the captured packets confirms whether the FortiGate is sending tunnel packets to the correct AFTR address. The third issue category is NAT and policy configuration problems. If the firewall policy is missing or has NAT disabled, LAN clients will not be able to send traffic through the tunnel. The command diagnose firewall iprop shows active NAT sessions and can help confirm whether NAT translations are occurring. Also verify using get firewall policy that the policy from LAN to DS-Lite tunnel exists and has NAT set to enable. MTU issues represent the fourth common problem category. DS-Lite adds 40 bytes of IPv6 overhead to every packet. This means the effective MTU for IPv4 traffic through a DS-Lite tunnel on a standard Ethernet link with an MTU of 1500 bytes is reduced to 1460 bytes. Applications that send large packets without path MTU discovery may experience fragmentation or silent drops. You can address this by configuring TCP/MSS clamping on the DS-Lite tunnel interface with the command config system interface. Edit DS-Lite tunnel, and set TCP/MSS 1420 to ensure TCP connections negotiate a maximum segment size that fits within the tunnel MTU. MTU and MSS in DS-Lite tunnels. One of the most operationally important aspects of DS-Lite deployments is understanding how encapsulation overhead affects the maximum transmission unit, or MTU, of the tunnel. If this is not handled correctly, users will experience intermittent connectivity failures, slow page loads, and applications that partially work but fail to transfer large amounts of data. These problems are often misdiagnosed as ISP issues or application bugs when the root cause is MTU fragmentation within the DS-Lite tunnel. To understand the problem, recall that standard Ethernet carries a maximum payload of 1500 bytes. This is the standard MTU that most networks are built around. Every IPv4 packet must fit within this 1500 byte limit when traversing an Ethernet segment. When DS-Lite encapsulates an IPv4 packet inside an IPv6 packet, it adds a 40-byte IPv6 header to the front of the existing IPv4 packet. This means that a 1500-byte IPv4 packet becomes a 1540-byte IPv6 packet after encapsulation. A 1540-byte packet cannot traverse a standard 1500-byte Ethernet link without being fragmented. The consequence is that the effective maximum transmission unit for IPv4 traffic through the dual-stack Lite tunnel is 1500-40, which equals 1460 bytes. Any IPv4 packet larger than 1460 bytes that enters the tunnel will need to be fragmented before it can be carried across the IPv6 access network. Fragmentation introduces processing overhead at both the B4 and AFTR, and certain network paths drop IP fragments entirely, causing connectivity failures for large transfers. The most reliable solution is TCP/MSS clamping. MSS stands for maximum segment size and is a TCP option that two endpoints negotiate during the TCP three-way handshake to agree on the maximum amount of data each TCP segment will carry. By configuring FortiGate to clamp the MSS to 1420 bytes on the DS-Lite tunnel interface, you ensure that TCP connections established through the tunnel will never generate segments large enough to require fragmentation when encapsulated. The value of 1420 is calculated as 1460 bytes of IPv4 MTU minus 20 bytes for the IPv4 header and minus 20 bytes for the TCP header, leaving exactly 1420 bytes for TCP payload. IPv6 prefix delegation alongside DS-Lite. DS-Lite solves the problem of IPv4 connectivity over an IPv6 access network, but a complete modern deployment should also give LAN clients native IPv6 addresses for direct IPv6 internet access. This is achieved through DHCPv6 prefix delegation, often abbreviated as DHCPv6PD, which is defined in our FC 3633. With prefix delegation, the FortiGate requests a block of IPv6 addresses from the ISP DHCP-v6 server, and the ISP delegates an entire prefix, typically a /56 or /48, to the FortiGate for use on the LAN. The FortiGate then subdivides this delegated prefix into smaller /64 subnets and assigns one /64 to each LAN interface. LAN clients use Slack or DHCP-v6 to obtain addresses from this delegated prefix and can communicate with IPv6 internet destinations directly without any NAT or tunneling. Let me walk through the architecture diagram. The ISP DHCPv6 server delegates a prefix, shown here as 2001:DB8:ABCD::/56, to the FortiGate WAN interface. The FortiGate takes this delegated block and carves out a /64 subnet for each LAN segment. In this diagram we see LAN subnet A receiving 2001:DB8:ABCD:0001:/64 and LAN subnet B receiving 2001:DB8:ABCD:0002:/64. Both subnets connect to the FortiGate, which provides the default IPv6 gateway and forwards IPv6 traffic from LAN clients directly to the IPv6 Internet without any encapsulation or NAT. The DS-Lite tunnel continues to handle IPv4 traffic in parallel through the same FortiGate device. This dual-path architecture is the standard deployment model for modern DS-Lite installations. Native IPv6 through prefix delegation for IPv6 traffic and DS-Lite tunnel for legacy IPv4 traffic. Configuring prefix delegation on FortiGate requires adding the IP6 delegated prefix list configuration under the WAN interface and referencing the LAN interfaces that should receive sub-prefixes. The FortiGate automatically handles the sub-prefix assignment and advertises the prefix to LAN clients via router advertisements. QoS and traffic shaping for DS-Lite. When all customer traffic flows through a DS-Lite tunnel, traffic shaping and quality of service policies must account for the tunnel encapsulation. This is a subtle but operationally important consideration. Without careful quality of service design, voice and video traffic that requires low latency and consistent throughput can be disrupted by bulk downloads competing for the same DS-Lite tunnel bandwidth. The challenge with DS-Lite and QoS is that DSCP markings in the inner IPv4 header, which is the original customer traffic, are not automatically copied to the outer IPv6 header that carries the tunnel. The ISP's network equipment only sees the outer IPv6 header when making forwarding and queuing decisions. If the outer header carries no DSCP marking, the ISP network will treat all DS-Lite tunnel traffic with the same priority, regardless of whether the inner payload is a voice over IP call or a file download. FortiGate addresses this through its traffic shaping framework. The configuration shown on this slide creates a shaping policy that matches traffic types based on application or service and assigns them to different traffic shaping profiles. The shaper named DS-Lite Priority is applied to traffic on the DS-Lite tunnel interface and limits total tunnel bandwidth to the provisioned WAN speed, in this example 100 megabits per second. Within that total, a guaranteed minimum of 20 megabits per second is reserved for voice traffic, ensuring that even during periods of heavy data transfer, voice calls maintain adequate bandwidth and low latency. The per IP shaper shown in the second block of the configuration limits each individual LAN host to a maximum of 50 megabits per second through the tunnel. This prevents any single user from consuming the entire DS-Lite tunnel capacity and starving other users of bandwidth. FortiGate applies this shaping before encapsulation, meaning the rate limiting occurs on the inner IPv4 traffic before the 40-byte IPv6 header is added. DNS considerations in DS-Lite deployments. DNS configuration in DS-Lite deployments requires careful planning to avoid subtle but impactful performance and compatibility problems. Because DS-Lite creates a dual-stack environment where both IPv6 and IPv4 services are available to LAN clients, the DNS resolver behavior determines which protocol is used for each connection and can significantly affect the user experience. The first DNS consideration is resolver selection. LAN clients in a DS-Lite environment will typically have both IPv4 and IPv6 DNS resolver addresses available through DHCP and router advertisements respectively. The FortiGate itself can serve as the DNS proxy for LAN clients, forwarding queries to upstream resolvers. You should configure FortiGate to use DNS resolvers that are reachable over IPv6 to avoid all DNS traffic consuming DS-Lite tunnel capacity. Google's public IPv6 DNS resolver at 200.1:4860:4860:8888 and Cloudflare's resolver at 2606:4700:4700:1111 are both excellent choices for upstream resolution over native IPv6. The second consideration is the Happy Eyeballs algorithm, defined in our FC 8305. Modern operating systems implement Happy Eyeballs to handle the scenario where a hostname resolves to both IPv4 and IPv6 addresses. Rather than trying one and waiting for it to fail before trying the other, Happy Eyeballs initiates connection attempts to both addresses nearly simultaneously and uses whichever responds first. In a DS-Lite environment, native IPv6 connections are always faster than IPv4 connections through the tunnel because IPv6 does not require encapsulation overhead and NAT at the AFTR. Happy Eyeballs naturally prefers IPv6 in this scenario, which is the desired behavior and helps reduce DS-Lite tunnel load. The third consideration is DNS64 and NAT64. Some DS-Lite ISPs also deploy DNS64 and NAT64 to allow IPv6-only clients to reach IPv4-only servers. DNS64 synthesizes quota records for IPv4-only hostnames by prepending a well-known prefix to the IPv4 address, and NAT64 translates IPv6 packets destined for those synthesized addresses to IPv4. This is a different mechanism from DS-Lite but can coexist in the same network. DS-Lite security considerations. DS-Lite introduces several security considerations that differ from traditional IPv4-only deployments. Because all IPv4 traffic is encapsulated inside IPv6 and traverses the ISP network before being NAT at the AFTR, the security model has different characteristics compared to a deployment where the customer has a dedicated public IPv4 address. Understanding these differences is important for designing a secure DS-Lite deployment on FortiGate. The first security consideration is inbound attack surface. In a traditional deployment where the customer has a dedicated public IPv4 address, attackers can target that specific IP address with port scans, brute force attacks, and exploit attempts. With DS-Lite, the customer does not have a dedicated public IPv4 address. Instead, the customer shares a public IPv4 address at the AFTR with many other customers. This shared address model means that port-based inbound connections from the Internet to LAN devices are not possible by default, because the AFTR has no port forwarding rules configured for individual customers. This provides a natural protection against unsolicited inbound IPv4 connections, which is beneficial for security but prevents legitimate use cases like hosting servers or using applications that require inbound port forwarding. The second consideration is IPv6 attack surface. Because the FortiGate WAN interface has a globally raw table IPv6 address, and because LAN clients with prefix delegation also have globally raw table IPv6 addresses, the IPv6 surface is fully exposed to the Internet unlike the IPv4 surface. This is a significant change from many IPv4 deployments where all LAN clients hide behind NAT. You must ensure that FortiGate firewall policies properly restrict inbound IPv6 connections from the Internet to LAN devices. The configuration should explicitly permit only expected inbound IPv6 traffic such as ICMPv6 for network diagnostics and explicitly block everything else. The third consideration is tunnel inspection. FortiGate's deep packet inspection and UTM features operate on the inner IPv4 payload of DS-Lite traffic. You should apply antivirus, IPS, web filtering, and application control profiles to the firewall policy governing DS-Lite tunnel traffic to ensure that encapsulated traffic is subject to the same security scrutiny as any other traffic type on the network. DS-Lite with FortiGate HA and Best Practices Summary. For deployments that require the highest levels of availability, FortiGate supports high availability clustering in both active-passive and active-active modes alongside DS-Lite. Understanding how HA interacts with DS-Lite tunnel state is essential for designing a reliable deployment that can survive individual FortiGate hardware failures without requiring manual intervention. In an active-passive FortiGate HA cluster, one unit is active and handles all traffic while the second unit is in standby mode, continuously synchronizing state from the primary. The synchronization includes session tables, routing tables, and interface configurations. When the active unit fails, the standby unit takes over and inherits the complete network state including the DS-Lite tunnel configuration. Because the DS-Lite tunnel is a software tunnel rather than a hardware interface, the failover process reestablishes the tunnel on the new active unit using the same configuration. The AFTR at the ISP sees a brief interruption as the failover occurs and then receives new tunnel packets from what appears to be the same V4 endpoint because the virtual MAC address and IPv6 address are preserved across the failover. The best practices diagram summarizes all the key recommendations from this series in a structured view. Let me walk through each element. The WAN interface connects to the ISP and should be configured for DHCPv6 to receive both the WAN IPv6 address and, where supported, the AFTR address via option 64. The DS-Lite tunnel interface should have TCP/MSS clamping set to 1420 bytes to prevent fragmentation issues. The LAN should run DHCPv6 prefix delegation for native IPv6 connectivity alongside the DS-Lite IPv4 path. DNS should prefer IPv6 resolvers to keep DNS traffic off the tunnel. Traffic shaping should be applied to guarantee bandwidth for latency-sensitive services. The link health monitor should continuously probe the tunnel path and trigger failover to a backup WAN if the primary path fails. Finally, firewall policies should apply full UTM inspection including IPS and antivirus to all traffic traversing the DS-Lite tunnel. Thank you for your attendance. Please consider subscribing to the channel and liking this video.